It is my pleasure to introduce Professor Thurman Lockhart. He is the Moore Foundation Professor of Life in Motion in the Biomedical Engineering program in the School of Biological Health and Systems Engineering at Arizona State University, and also one of our funded professors in the Brain Center. In fact, he started working with us since 2017 when the center was created with funding from National Science Foundation. He's also a guest professor at Ghent University in Belgium and a research affiliate faculty with the Mayo Clinic College of Medicine. He has many publications, and his research concerns the identification of injury mechanisms and quantification of sensorimotor deficits and movement disorders associated with aging and neurological disorders on fall accidents. And the project I'm going to present today is about fall prediction. So his work is very exciting, has received a lot of attention by both scientists and the media, and really my pleasure to introduce him. So Thurman, please go ahead.
Right. Thank you very much, Pepe. Well, thanks for the nice introduction there, Pepe. Pepe and I, we've been working together since 2017 on this brain project. And since then, we have gained a significant amount of knowledge in terms of transforming the research into reality. And that's basically what I wanted to kind of talk about today. And kind of dwell a little bit on the research side as well. And then, of course, provide you with a paper so you can read that and understand a little bit more. But today's discussion is really about brain project and how it really helped me as a basic scientist traveling towards the business area of murky, chaotic business area. So the title is called The Movement, Complexity, and Falls, and our website is nsfbrain.org. My name is Thurman Lockhart, of course. And here we're going to be talking about Lockhart monitor, a variety of illnesses or conditions that we could actually assess utilizing this system. But before even that, what I wanted to talk to you is a problem associated with the falls in elderly, and the genesis of this project, by the way, and leading into what we have now, the actual device. But before that, we had to do lots of basic research, perturbation research, and these kind of things to really understand the motor control aspects of reactive recovery and fall accidents. And then after that, I will talk about the brain project that was actually performed since 2017 and how this has improved our research and our throughput. In the world, fall accidents are second leading cause of death next to motor vehicle accidents, and now probably the COVID. There's a significant amount of falls. So who reports this? And that's very interesting. But more interestingly, in the U.S., we're not looking too good. This was in 2019, 39,000. Right now, it's about 41,000 persons have died in 2022, and this is continuously increasing. Hospitalized about 800,000, treated about 8 million. Okay. Cost us about $67.7 billion. Here's 28 projection, and here's 2030 projection. 2030 projection, what our U.S. government is saying is that there will be 52 million falls. 52 million falls. Just think about that. And so we have to do something about it. And these falls are not just in our elderly. It's not just about slippery surface. It's about a variety of different things. And of course, traumatic brain injury is increasing significantly as well. You could see the national average of a TBI, 29.6 per 100,000. Here in Arizona, it's 277 per 100,000. Similarly, in Florida, you'll see this as well. Why is that? What is going on? Well, and not only that, of course, once you survive the fall, it's painful. And not only that, about 20 to 30% develop this thing called the fear of falling, so they stay inside home, and sedentary aspects of life takes on from there. 20% die within a year and placed in a nursing home, so it's not a good thing. What we want to do is we want to avoid falls at all costs. Currently, in terms of our intervention, this is what it looks like. We have fall protection and fall prevention. Fall protection, guardrails, fall resting harness system to, help out with the, worker populations, helmets, hip pads, building codes. All of these things are there to a certain extent. Code of Federal Regulation tells us how to design this effectively and safely. So in essence, fall protection, we are doing pretty well. What we are not doing too well is in fall prevention, preventing to fall. Because you remember that once you have fallen, you get into all these kind of problems. So the key is to not get into that fall accidents. And how do we do that? Well, we understand by, for example, environmental control, coefficient of friction. We are currently working on a project with a CPSC, Consumer Product Safety Agency, in a baiting surface, because there is no standard currently. Standard that has been out there in the 1970s is obsolete. And as a result of that, there's a significant amount of death, especially older adults. And so we are doing some studies in that regard in terms of assessing friction demand and things like that. And there needs to be done more. This is just an example. Fall risk assessments. As you know, that there are a variety of fall risk assessments. A lot of them are questionnaires, mainly because the physicians do not have time, as I find out, as I go through this realm for 20 years, trying to find a cardiac surgeon and try to talk for 5 minutes is impossible. And the fall risk assessments are done very, very quickly. It's a Likert scale. Have you fallen before? Do you have urinary incontinence? And these kind of questions, and you add it up. If it's 10 or over, you're a faller. If not, you're a non-faller. Although it is somewhat effective, things like ABC score, activity balance and confidence score, some of them are not useful. And a lot of things are happening. A lot of research is going on currently in intervention strategy, strengthening endurance, balance, and also directly to brain. We're right now about to stimulate pedunculopontine nuclei as well as STN, subthalamic nucleus, both of them together in a Parkinson's patients, and we're going to be talking about that. So there are some neurotechnologies that are available for us for people like Parkinson's disease. People who are dwelling in a community who are weak, we could actually intervene very nicely with these proven exercises and regimens. And the brain, our brain research sits right in compendium crossroad of this right here. And that's what we're going to be talking about. But before that, let's learn a little bit about gait. And I always talk about this. Since you guys gave me about an hour, I'm going to talk about a little bit more. So locomotion is a characteristics of all animals. If you're an animal, you have to locomote. And for us, means to locomote is called striding bipedalism. And what you see here is called a striding bipedalism. You can see left and right. It's alternative, it's taking a strike there. This footprint, by the way, was created by possibly Australopithecus afarensis, Lucy, about 3.7 million years ago, not billion. And what happened was a plume of ashes fell down, volcano ashes, and then it kind of rained a little bit. It became a mud kind of like structure, like a sand, wet sand. These beings walked on it, and then a plume of ashes fell, and it solidified it. And what I want you to kind of gather here, and what I show here, is really this little footprint. walking with a big footprint. You can see the big footprint is taking a shorter step, whereas a little footprint is taking a longer step. Let's see if I can draw that. So what's happening here is this bigger being is probably carrying or holding this child being and walking across on this very slippery surface. So my question is this then. 3.7 million years ago, these beings, bipedal beings, walked on a very slippery surface without any problem. You could see that. There's no fall. It's a nice smooth gait. Why are we still falling? That's the key question. And think about that and put it in your head for a while. And why are we still falling? Well, the answer will come out pretty soon. And so if you look at it, carefully look at it, Shimba in 1981 studied the center of pressure as well as center of mass. And what they find out was that center of pressure at a base of support, our whole body center of mass is always outside of the base of support during our gait. So basically what's happening is every single time we're taking a step, we're falling and catching ourselves. And as a result of that, if you look at some phase diagram, for example, like leg angle, leg velocity, at certain instance, like a foot strike here, you could see some variability associated with that. This one right here is variability related to standing, just stance time, which kind of shows us a fractal like a pattern. So it is a fundamental motor behavior. And recently, a study in Nature they just come out, and looking at the mouse, they know that this program of exploring and escaping behavior through locomotion is structured right in the midbrain structure of rats, and right around where pedunculopontine nuclei as well as cuneiform nuclei is, and most likely that's the brain portion that does the exploration, the slow locomotion, as well as the impending danger. If the saber tooth comes in, you need to change that mode into a reactive recovery mode, and that might be occurring. The study indicated at that structure, that nuclei, and this is one of the reasons why Parkinsonians are having some issues with the gait and posture, and this is one of the reasons why we are going to test the deep brain stimulation in both of those sites. Pilot testing right now, submitting that into U01. Hopefully, some of you will be able to review. So this is a neuro talk, so I have to put some motor control stuff in there, and this is just simple motor control related to utilization of vestibular apparatus, and also basically we use everything: vision, vestibular, proprioceptive system, somatosensory, whatever have you. We utilize that information to locomote because it is a survival modality to a certain extent. Okay. So I was always, interested in this exploring behavior, normal locomotion, normal gait, and this escaping behavior as well, And what creates that? What kind of a hormone is released such that it changes that state? That still needs to be, it must be glutamatergic, possibly. Anyway, so that still needs to be answered a little bit. But now let's kind of get back into what we know for sure. We know that as we, age, we have degradation in sensory systems. Your vision, your vestibular, your hair cells, ciliary cell disappear. It doesn't matter how much you exercise, diet, take a vitamin, it's just going to go. So there's a sensory degradation. There's a cognitive impairment as well as muscle weakness. And as a result of that, possibly there is a gait adaptation. We take, wider base of support, shorter step length, slower walking velocity, but not only that, slower transition of a center of mass. And at this time, when I was doing my PhD dissertation, I was asking myself, why do older people fall more than younger adults? And so we have to do some of these kind of experiments. Oops, let's watch that again. You can see that nice hand reaction there. Using that information, you could do some nice modeling because they're wearing a harness, and to calculate what's happening at the bone, vertebral trochanter. So you could go forward fall. You could do a variety of falls. This one I want to show you because this is very interesting. You cannot see this, right? Oh, there it is. It takes a while. So this is 78-year-old female with Parkinson's disease, 10 years. The first perturbation was a fall. Second one, a little bit less. Third one, a little bit less. And so we actually apply this training to Parkinson's patients. And this is their data. And she says she had enough. And so there, we're perturbing these individuals, and then looking at their preactive and, in fact, not just reactive, but also looking at the pre and post. And so when you look at that, you can see here there's a significant influence in multi-scale entropy. So after you perturb these individuals, their gait pattern changes into this more random-like structure, which I will talk about a little bit later, which we call complexity. Probably some papers on it, and all those papers are there. And this is the mechanism that we learn. Here is an environment, initiation, detection, and recovery. Environment, it starts with a low available dynamic coefficient of friction, water, banana peels, whatever have you there, right? Or raised edge or whatever. There has to be some kind of environmental consequences or even internal perturbation as well, things like a syncope. So initiation of slip occurs whenever whenever you demand more friction than what is on the floor surface. And that creates the initiation of slip. And the initiation of a slip, well, what I hypothesized was that some of these parameters were influenced that initiation, things like step length, this gait changes. Maybe muscle changes can also change this initial dynamics, and maybe this is why older adults are falling more. That was the hypothesis. Well, after higher friction demand than what is available, normal friction demand for young adults are 0.18 to about 0.20. Just to give you a sense that a slippery surface vinyl tile with a soapy water is about 0.10. So if you demand 0.2 and what's available is 0.1, physics tells you that you will have a slip. But that's okay because you have encountered many of those kind of cases. You slip a little bit and then you recover. How did you do that? Well, you use your sensory mechanisms, your vision, your vestibular, your proprioceptive system, your Golgi tendons, muscle spindles, all those things stretching out gives this information, like I said before, in the midbrain structure, and then it changes that program to that reactive structure. And at this point, even if that reactive timing is appropriate, you have to have a counter-reactive force that can resist the perturbation. And so if you don't have that, then you tend to fall as well. So this is a paradigm that we usually work with. And this is the paradigm related to creating a wearable system to predict variety of conditions. So you could see here, if you want to find out fall risk, you want to assess their gait. You want to measure their sensory system. You want to measure something about their reactive recovery scenario. These two we have done very nicely. Gait speed, gait test and all that stuff. Detect, sensory, posture sway, all that stuff. Recovery, however, is a key question. How do we do that? Well, that in itself was the essence of our project for about 8 years, funded by NSF, and using nonlinear dynamics as well as chaos, the up and up exponent, to actually simulate this reactive recovery scenario such that utilization of that parameter can actually predict future fallers. We'll talk about that story here. Going back to the initial gait characteristics, here's what it looks like. Force play, that you have this usual M and of course horizontal force. Your friction demand actually occurs about right here, 0.3. And so you can see clearly heel contact, and then after about 100 milliseconds, that's when you start to slip. So initially what I thought was people would slip, grab it, right there and then slip. And this is why people thought heel velocity was an issue and things like that. But no, heel is contacted and is momentarily hovering, and you don't slip for about 110 milliseconds until the center mass comes over, utilizing this push off from this gastrocnemius. And so this foot will come off and the center mass rotates. And that in itself is related to slip initiation. And so here, what I want to show you was that as we slip, and this is what I was able to simplistically model back in 2008. As you slip, your center of mass gets closer to the base, and as a result of that, your friction demand, your coefficient of friction decreases, and that's why you slip stop. And of course, our movement is always up and down. And what we're finding out is that it's really not the heel velocity. It is about the center of mass, shifting of the center of mass. If you can shift that center of mass faster, then you decrease this friction demand very quickly. And that's that's the strategy adapted by young individuals. Strategy adapted by older adults are somewhat proactive, like walking slower. Here's older adult, younger adults. And friction demand lower, 0.15, because they're walking slower, more vertical force, less horizontal force. So then you can see clearly older adults are adapting. Their adaptation of gait is all directed toward stabilizing themselves. Wider base of support, slower gait speed, shoulder step length, everything is related to making them safe. Mainly, and how did that occur throughout these years? Well, most likely these individuals felt it. Loss of, someday when they wake up, their vestibular system start acting out. So they start to walk a little bit differently, perhaps. Regardless what it is, as we get older, we adapt without even knowing it, and maybe is related to our sensory degradation, most likely. And looking at the EMG profile, you can see clearly your muscle profile plays a significant role. Here, basically, what I'm showing you is exactly the same theta 1 and theta 2. If you can move from theta 1 to theta 2 faster, then your likelihood of slipping and falling decreases, right? And that's what the younger people are doing. Older people are, because they're walking slower, even though they have a slower heel velocity, because they're walking slower, they're in this domain, theta 1, a little bit longer, which requires more friction, horizontal force. And that's all it takes. And then from there, because of their muscle weakness, they're not able to create that reactive rotating torque. And that's what I found out. And not only that, it seems like there's all kinds of different, you know, strategies as well. Upper limb strategy, lower limb strategy, the whole body strategy. And the strategies are brought on without even teaching. And it's innate within us. And so this person is actually going to stop this fall by using everything. Head, arm, right? When you do that, big mass head, center mass transitions forward, and then arm comes up, transitions forward. And this is what it looks like. Bottom line is younger people can slip, 3.91 centimeter at 144 centimeters per second and not fall. The older person falls, a little bit less here. And the regression model shows that, muscle, leg muscle, more importantly, and the reaction time and your vision is very, very important for maintaining that slip distance. So this is the bottom line. The bottom line is this, and then here's all the muscle activities and everything. Here's younger adults and older adults. Younger adults and older adults, about the same, start, slip, in the mid-slip. The difference of import really occur here, slip, stop. And that's reactive recovery. And related to all of the scenarios as we discussed. And then so, after about 10 years of this, we have gone through more than probably 500, 600 people going through slips and falls. We learned something. Published some papers and things like that. But we learned that, the control system has a finite time delay, right? And it also responds to the sensitivity to initial conditions. So, for example, if I make this individual fatigue, leg fatigue, which we have done before, do some squats and everything, and then have them go through this scenario, they fall more. So it is sensitive to a certain thing. And given this kind of idea, we're now trying to create a model that computational model that can help us look into the mechanisms. So we down on this nonlinear time delay coordinate system, so used by a variety of scientists in this domain. And Kevin Granada was my mentor at that time, before he passed away at Virginia Tech. And then, of course, Dingwell, and, we all kind of, Dingwell and I think, won the Whitaker Biomedical grant, the last one. And I know he was doing some great work with the Leopold and things like that. So here, the bottom line is this. So we know that there's instability. How are we going to model this instability to a certain extent? And given this kind of information, how robust is that model? So we apply this thing called the Leopold exponent, and it's a chaos measure. And basically what we do is we get an original time series, any kind of a time series data, accelerometers or marker data, it doesn't matter. We go through all the mutual information, nearest false neighbor method, to actually kind of decompose some of these data, because we're gonna actually reuse some of this data, such that if the message repeats itself, then it's not going to help us. So we're trying to find that optimal criteria with the time delay and then embedding dimension. So for a gait, we use about 10 time delay and 120 hertz. And then we go all the way up to about 5 dimensions of that. We reconstruct state space there. We apply Rosenstein algorithm, and then we calculate Leopold exponent. And since this is a educational type of modality, I'm going to go through Leopold exponent on how we calculate. So here's a time series data that you will see, accelerometer data, whatever have you there. And then basically this is the time delay. Here I'm using just 2. And then here's dimension. I'm using just 3 because I cannot, how are you going to graph 5D? Well, maybe you can. Anyway, so, and then you grab this set of data. Like I said before, we got all the way 5D, and ours is more like 10 or 12. This is just an example. And then basically we look at a distance somewhere, and we look at this distance nearest neighbors, and then we basically count the distance. And we do this recursively over and over and over and over and over again. You remember Wolf's method too, also, to a certain extent. Used to take us, 2-3 hours sometimes. And once you have all of this, and then you get a slope, right? So basically what it means is if there's a diverse pattern, this will be higher. So meaning it's higher slope. If this is not diverse pattern, or it's all one line, it'll be very low, right? So the slope tells us how stable you are in terms of the changes to that initial condition. And we apply that to older adults, fall-prone older adults, and the healthy older adults, healthy young individuals. And we're able to publish that back in 2008. And we say, wow, this is a great tool. Let's apply this. And so we apply to a variety of things as well. Just recently, we applied this to finding exoplanet, just to kind of tip it. Here's a Lorentz attractor, chaos, 8.254. So it is a chaotic, and it diverge, right? So it means that given a initial position, perturbation, it'll deviate, perhaps come back. Here is radial velocity. Radial velocity is kind of an interesting thing. I'm kind of getting into it. Basically what they do in Chile and places like that, they have microscope. They look at a star or sun. And basically what you're looking at is a shifting. And it's just a sound. Pink noise going away, blue noise coming in. Kind of like, whoom, that car comes and goes away. That's what you see. Well, how do you see that? Well, because that star is here. If there's a planet, it's going to go around it. And as it goes around, it pulls the sun. And for us, only thing we can look at is this to a certain extent, right? Radial velocity. And radial velocity of this system looks something like this. And we apply Lyapunov exponent, and sure enough, we got a convergent characteristics of negative 26.3, meaning that given a perturbation of this planet, it's not going to veer away from that star. And I think subsequently right now, we're writing a paper, we could actually calculate the mass, I believe, using mass of the exoplanet system, using this. So it is a nice measure that works in human beings as well as the cosmos. And then we start to get it. So we have a very nice measure there. And now we start to kind of, get into, what happens when a person is actually, perturbed. And if that person has some kind of a limitation, what would that limitation look like? And we know what that limitation looks like. That limitation is somewhat like a robotic kind of gesture, movement. You get a very old individuals, you make them slip, they will jump. It's got a lot of jerky thing happening there. Whereas a younger person, smooth repertoire, right? So we start to kind of delve into understanding entropies. And entropy has been measured previously to assess complexity by Goldberg and these guys. So what you're looking at here is dendritic arbor in belt cell. And here's a young person, which is somewhat complex. And here on the right is older adults here. So what we're saying is overly structured, stable, unchanging patterns suggest that control processes are rigid and may not be adaptable to change or perturbation. So in this system here, if I give it a perturbation, to react to that, it'll take a longer period of time, possibly, than this system. And we wanted to see if this occurs with other system as well, not just the brain, heart rate, gait. And so, of course, they haven't looked at it. Right? Gorber, 1992, looked at heart rate. Back in those days, they were doing approximate entropy. And there's some, approximate entropy is good. So here, you got a heart rate 64, standard deviation 3.9, exactly the same. What he's trying to show you there is that approximate entropy is the real variability. It's not the standard deviation to a certain extent or variance. It is the approximate entropy. So here is 22-year-old female with a healthy heart, and here it is unhealthy heart. Indeed, looks somewhat robot-like. So the complexity is low. Given a perturbation to this system, not responding perhaps back. Happens in also posture stability as well. This is a dwell time we measure for 30 seconds and shows that fractal pattern. This is fallers and non-fallers, approximate entropy, and then we start doing sample entropy in this manner. You can see clearly fallers exhibit less complexity than non-fallers. So we start to look at heart rate intervals. People calculate that all the time. And mainly one of the reasons that we want to calculate this is because later on I'm going to be talking about the brain project. And, oh, geez, I think I'm almost over time, so I've got to go quick here. But the entropy shows there is an aging effect. Multi-scale entropy, you can see clearly there's differences there. So this is what we call nonlinear dynamics. It's not really a chaos, but complexity measures can show some system dynamics very nicely. And the maximum Lyapunov exponent also shows that as well. And so what we are doing with it? So from understanding from this phase of gait and understanding biomechanics of gait, start doing perturbation tests to understand variability structures, and then understanding that mechanism through nonlinear dynamics and chaos, and then bringing this to a sensor is what we did. Okay? So for last about 12 years, we've been developing a variety of sensors, incorporating into Lyapunov exponent. We also use flow K multipliers and a complexity, spatial temporal gait parameters. And we used to do with the watches and things like that, but we just settled on the phone. And published some nice papers of looking at the Lyapunov exponent as well as flow K multipliers, looking at the drug effects. We were able to do that. So, and the fall risk assessment, of course, we are able to. This is a recent publication. We're able to use this system to actually predict fallers, people who has not fallen. And you could read this paper, the accuracy and everything is reported. And now I'm going to talk, having all this information, we start to help out with brain project. The first thing was the brain community want us to basically validate the heck out of it. We told this story, they say validate it. Validate it on a variety of patients, not just elderly, people with total knee replacement, hip replacement. So we are collaborating with the Core Institute and Mark Jacoski. There he is. Mark Jacoski and Core helped us significantly. Claire, of course, was one to help us here, and Andy at the first time. And we got this Grail system, so we could perturb these individuals and then measure their complexity and things. And sure enough, maximum Lyapunov could give you some idea of fallers and non-fallers. This is actually a perturbation study. And then after doing massive amounts of validation for about 2 years, we start to kind of utilize, and Mark had a great idea to utilize this into their system. Of course, he probably had that in mind many, many years before choosing this. And why is that? Well, because the prehab exercise, right, range of motion after the surgery is significantly lower. Prehab is working out. So prehab, they're already doing this. They're already collecting this. So their problem was, how do we make these people really do a prehab, and also how do you measure these things, and even at home. And so we start to use Lockhart monitor, and the Lockhart monitor looks like that. And the free version still is out there, Lockhart monitor. And then of course, this is where the brain comes in. Brain converts that into a company, and now you got people from company coming in. You got people from financial institutes coming in, and we could do very nice things. Telemedicine. So this system is going to be actually being used. Change it name into MyActome. Created a company, and it collects the data of this individual. I'm going to just kind of go through very quickly. Do not copy this. Clinicians are going to be using this, and you could go to individual clinician and their patients, how they're doing, test history, time up and go, sway, balance, complexity, what we call kind of a steadiness. And then it throws out mobility reports. But more important that, utilizing that information and just a little dot that we have created, we could actually use this to exercise. So we're creating this modality right now. And we are also helping with HIGIPAN, sideline concussion assessment. And this is why it's so important to measure heart rate, because these guys are going to be running. And then when they come to the sideline and when we test this, we have to understand the heart rate effect. And so we help them with that. And the most interesting thing that I think we're about to do is measuring depression with the spatial temporal gait parameters. We have some animal study behind this, what to look for. And of course, this is the key here, and looking at the complexity. Actually, also RQA, a variety of nonlinear dynamics we're going to be using to assess behavioral patterns, and that's coming out soon. Yeah, that's all I have for now. Thank you very much, and I will just wait for some questions.
Wonderful. A little bit of applause from everybody here.
Oh, thank you very much.
Okay, so do we have questions? Feel free to unmute yourself or just put them in the chat. So Taylor has a question. Taylor, do you want to unmute and ask it, or I can also read it?
Hi.
Yeah.
Can you hear me?
Uh-huh.
Hi, thanks for that talk. I was wondering, when you do identify someone as high risk for falling, what kind of interventions can they use in their lives to not fall?
Yes. Right. And so that's what, we're trying to do here. In fact, we are right now creating modalities, exercise modality. So let's say, for example, you measure posture stability and you have some issues with posture stability, maybe vestibular or maybe, your vision possibly. And so there are some exercises that you could do, with you stand up and you hold onto this table and you lift one leg and move your head side to side and, doing this kind of things. There are a variety of exercises that are available. And so we're going to incorporate that into the app. So once they measure the scenario of exercise scheme will come out. And it'll be a video coming out and things like that, which is all based upon CDC guidelines and things like that. So yes, once we know if you have a gait problem, if you have a strength problem, or if you have a balance problem, what we have done so far well, very well, is coming up with this intervention schemes, exercises. We're very good at it. There are a variety of exercises. If you're too frail, you could still do exercises in a variety of modalities as well. So that's the thing. Number one, identification is number one, and then second thing is to motivate these individuals to actually do some exercises. And then hopefully we could help out in that aspect.
Thanks.
Did I answer your question?
Yeah, that was great. Thanks.
Great.
All right, I have a question as well. So, in regards to Georgia Tech trying to join the IU CRC, I'm just wondering, do you have any advice for people, either faculty or students, but mostly students maybe, if they have ideas about projects or things that can become commercially viable, what are your piece of advice there?
Yeah. So, I mean, the Lockhart monitor, the original Lockhart monitor, that's been out there for a while. And the reason for that is because I myself tried to do it, promote it myself. This was a Lockhart monitor. It's still available. And I did all kinds of different presentations, hundreds, literally not 100, maybe, 90. Enough such that people are, as soon as I walk up there, they're saying, "Oh no, not the app again." From Mayo Clinic, I heard this actually, and imagine that, hearing that and then going up there, and I did it, presented, but really nothing happens until somebody really notices you to a certain extent. And that gentleman was this guy right here. So so it was this device right here initially, and then you look at what's happening now. Look at that, beautiful idea. And it's a reality, right? They're going to actually use it in their, their clinics and things like that. And then hopefully, there are some exit strategies and things like that. Right? So what I'm saying is, as researchers, we see certain things and we think that it's going to work for this purpose. But when you mix in with the business individuals who have some idea of technology, they were bringing a completely different set of ideas to a certain extent, and bring you to that reality. But the key question, suffering, is that you have to let it go. You have to let your science go, because what I did for the last 10 years was I was just holding on. I'm going to do it myself. Do this. You got to let it go. That's the thing. So soon as I let it go, collaborate with other companies, we start to actually, enhance ourselves. And so then, for all those students who have some ideas, I would say going through this kind of a program is amazing. And talking with industry leaders about your products, make sure you have an NDA. And all that stuff is placed with the brain, and that's why it's so nice, because you don't, as a researcher, that's what I was worried about. Are they going to steal my idea and then they're just going to go away with it? Well, brain has a structure such that I felt more comfortable sharing everything that I had, with Mark, and because of that, Mark and all of my graduate students and everybody who's involved, by the way. I mean, Chris Frame, Raul Soangra, Jen Liu, Victoria. I mean, Mark, all of these guys are involved. My students, everybody's involved in this. And being able to clearly communicate is the key. And having that extra set of eye from a business point of view is really a blessing in disguise. I hope that answers some question. Maybe too long.
Yeah, I think it did. It's definitely a wonderful success story. All right, other questions? Okay.
Right.
So seeing none, I want to thank you again